Hello everyone, it's a pleasure meeting you all in my mathematics class. Do not forget to subscribe for my channel, as you would definitely be gaining on watching my videos. My videos will definitely help the students who are in engineering college or in arts college or even in plus 2. So keep watching my channel and subscribe for my channel. So today I have taken a set G which consists of 4 elements, namely 1, minus 1, I and minus I. Where this I, as you all know, that it is an imaginary number. This I is an imaginary number which is given by square root of minus 1, because square root of minus 1 is not known. We do not know what is the square root of minus 1. So we call it as an imaginary number. And this I, if you square it, it becomes minus 1, and I cubed is minus I, and I to the power of 4 is 1. Now I do the ordinary multiplication. I define a binary operation. That binary operation I will call it as dot. Here this dot is nothing but the multiplication, which is the binary operation. This is defined on this set 4 elements, and the multiplication table I have given here. The multiplication table I will say, for example, you can find that this is 1 minus 1 I minus I. 1 minus, so 1 into 1 1, 1 into minus 1 minus 1, 1 into I 1 into minus I is minus I. When you multiply with this I into 1, everything, I into I is I squared is minus 1. I into I minus I, you get it as minus I squared, that is equal to plus 1. And this is minus I, this is plus I, this is I squared is minus 1, minus into minus is plus. So you see that I am able to give this matrix of elements by using the multiplication, ordinary multiplication. We have to prove that this is a group. It is very, from the table itself we can see that this is a group, because it satisfies all the 4 properties required for a set to be a group. So what are the properties? Closure property is satisfied, I will take here. What is the closure property? You take any 2 elements. That means you take A and B, you take A and B and do the dot operation. Dot operation is nothing but your ordinary multiplication, and this A dot B is equal to another element C, which lies in the set G. This is true for all AB. A comma B belonging to G. So this is true for any element you take. You see that when you multiply, it lies in the same element set, and therefore this closure property is satisfied. That is point number 1. It is satisfied. Okay. So this is satisfied. Come to the associative property. I will take an example. You see that I dot minus I dot minus 1. What is this equal to? I dot minus I. I dot minus I is equal to 1 into E dot. 1 dot minus 1 is equal to minus 1. See? Keep this. I will go for the association. I dot minus I dot minus 1. So what is this? This is I dot minus I dot minus 1. Minus I dot minus 1 is I. So this is your I. I into I dot I. See, I dot I is equal to minus 1. So here you see that this is also minus 1 and this is also minus 1. This is true for any 3 elements that you are going to take. That means associative property holds good. Therefore, we say that A dot B dot C is equal to A dot B dot C for all A, B, C belonging to G. So this associative property holds good, and we say that, and therefore you see that this property is satisfied. Since these two properties are satisfied, this becomes a semi-group. So we can call this as a semi-group. Not only that, now you go further, that this acts as the identity element. See, 1 belonging to G is the identity element. This is very obvious. See, 1 into anything is the element. I write it here. So this 1 into anything is itself, therefore identity element is. So this condition, this property is satisfied. Therefore, this G dot now becomes a monoid. It's a monoid in the sense that associative closure property is satisfied, associative property is satisfied, and identity element exists. Therefore, this is a monoid. And one more property, let us check for one more property. What is that? Existence of inverse elements for every element. Existence of inverse element for every element. Now, if we want to check that, what is the meaning of an inverse element? If A is an element and A dash is its inverse, then A dot A dash must be equal to E. Here A dot A dash, A is the element and its inverse is A dash. Then A dot A dash, and this must be equal to A dash dot A also. Now you can find, that means here E is equal to 1, identity element is equal to 1. So you go to this identity element, here 1, and here 1, and here 1, and here 1. So for this 1, the inverse is 1. For minus 1, its inverse is minus 1. For I, its inverse is minus I. For minus I, its inverse is I. That means for every element, it has its inverse in the same set. Therefore, or the inverse elements also present, the fourth property is satisfied, and therefore this becomes a group. That is 1 dot 1 is equal to 1, minus 1 dot minus 1 is equal to 1, I dot minus I is equal to 1, minus I dot I is equal to 1. So this tells us that this 1 is the inverse elements present. Inverse element are present. Inverse elements are present, and therefore, since four properties are satisfied, this becomes this G dot has become a group. Not only that, so I have proved that this is a group. Moreover, you will find one more property. Namely, see, you can just check this. See, A dot B is equal to B dot A for all AB belonging to G. See, this is very clear. See, I dot minus I is equal to minus I dot I. See, I dot minus I is 1, minus I dot I is 1. So this is true for all elements. Therefore, G dot is a commutative or an abelian group. You call it as an abelian group or a commutative group. So this is a very important problem from the examination point of view. This may be even for engineering students and also for arts college, and also even +2 students, they are supposed to know this. So this is an important aspect. This gives you a larger idea about what is a group and everything. And incidentally, know that you go for this. See, if you take I is there, and I squared is equal to minus 1, I cubed is equal to minus I to the power of 4 is equal to 1. So you see that if you take this I will generate the whole set. I dot I is equal to I squared is equal to minus 1. I squared dot I is equal to minus I squared dot I squared is equal to 1. So you see that the whole set can be generated by I. That is, therefore, this is a, see, G dot is also a cyclic group as I generates the whole set. If I is a generator, even you can just check that its inverse minus I also generates. Is also a generator. Inverse. The inverse also, that is here, I will write it here. I is the generator. I is the generator. Since I squared is equal to minus 1, I cubed is equal to minus I to the power of 4, 1. See, all belong to G, and therefore, see, I is a generator because of this reason. Also, its inverse minus I also generates the whole set. Therefore, G dot is a cyclic group. So this is all about this particular problem. I will tell you one more, I will give you one more idea on this. With this I will stop this class. See, here you see that I take, see, it's obvious that I write here, see, let H be equal to 1 and minus 1, and H dot is a subgroup. Why it is subgroups? Because see, the 4 properties are satisfied for a group, and since H is a subset of G, H dot is a subgroup. See, H is a subgroup because there are only 2 elements, and you see that here if I say that this is a subgroup, you can see that this H, 2 elements, or it is a subset of this, because here this contains 1 minus 1 or elements of G, and H contains these 2 elements, therefore this is a subset of this. All the elements of H are present in this, and I take the same operation dot. Now you do the operation 1 dot 1 is 1, so in the set 1 into minus 1 is minus 1, it is there, and the identity element is 1. Okay, that means 1 into 1 is 1. What is the inverse, and what is the inverse of 1? 1. What is the inverse of minus 1? Minus 1. So the 4 properties, closure property satisfied, associative property satisfied, the identity element is present, and inverse elements are also present. Therefore, H is a group by itself under the operation dot, and since all the elements are elements of G, this H is a subgroup of G. Okay. Now we define a coset. We define coset as, let G star be a group and H belonging to G be a subgroup. H contained in G is a subgroup, and H star. It is also the star. H star is a subgroup. Let for any A belonging to G, AH which is equal to A into H, where H runs over G, is called left coset. And HA is called right coset. So you see that how I define this coset. I take the set G and take the subgroup, take the set group G, and I consider a subgroup H, and H is a subgroup under the same operation. I take an element in G and form a group form AH. AH is a set which consists of elements of the form A into H, where H belongs to H. So if there are, for A it is one left coset. If you take another element B, for BH will be another coset. So you can form as many cosets as possible as there are elements in G. That is, you can form as many cosets as possible as there are elements in G, and this is called a left coset and this is called a right coset. Okay, so this is the idea of a coset. Now, what I do here is, in this particular example, see here what we do is, see here I take H is equal to, what is your subgroup? See, G is a subgroup. G dot is a group. Here G dot is a group. H dot is a subgroup where H is equal to 1 minus 1. Now, for I belonging to G, IH is the left coset, that is equal to I into minus I. Minus I belong to G, minus I into H will be equal to minus I, it is plus I. 1 belongs to G, therefore 1 into H is equal to 1 minus 1. Minus 1 belongs to G, therefore minus 1, H is equal to minus 1 plus 1. 4 coset, 4 left cosets. But see, call this as 1, call this as 2, call this as 3, call this as, see, but 1 and 2 are the same. 1 and 2 are identical. And 3 and 4 are identical. Therefore, there are only 2 distinct left cosets. They can also be right cosets. They can also be right cosets. And this G is equal to union of, see, it is the union of the, see, these two enough, see, these two of, see, what is this? IH. I can put it as what? Yeah, IH, IH union 1H. So you see that this whole set G is nothing but union of IH union 1H. See, IH is this and 1H is this. So you see that the union of these two is nothing but the whole of the set. Therefore, I will write it here. Therefore, Therefore, the cosets formed can be either identical or disjoint, and G is equal to union of A runs over G. And see, you have to, this is the union of all AH, where n is taking, considering that is a considering the fact here this is considering the fact 1, considering the fact, I will call it as A, considering the fact A. So this is an important one. With this I close down my class, and do not forget to subscribe on my channel to view more of my videos in the coming days. Keep watching. Thank you.